Hello everybody. In this lesson we will talk about the definition and basic properties of polynomial functions. So here on the very top of the slide you can see the definition of what a standard polynomial will look like. So y is a function of x and we have powers of x where n is an integer. So this is an important part of the definition. N is an integer. What does that mean? What can n be? N can be 1, 2, 3, and so forth, right? We of course will talk about finite degree polynomials. Okay, let's see. The degree of the polynomial would be the highest power of x. Okay, so degree is the highest power of x. So that's your maximum power. And we can also kind of decompose this function here. We have what we're going to call coefficients, right? So these are all numbers, right? So AI, I'm just using a subscript to represent these coefficients. These are real numbers. Okay, we're going to go ahead and identify AN as the leading coefficient. That's what we're going to refer to, as it's going to give us some information about how the polynomial behaves. All right, so let me go ahead and give you a couple of quick examples of polynomial functions. Some of the ones that we've been dealing with already, something like this, 2x squared minus 4x plus 1. So this is a polynomial of degree 2. Okay, let me give you another one. Something like this, negative 10x to the 9th plus 2x minus 5. Okay, so that's a polynomial of degree 9. And you can see how we're kind of skipping all of the powers of x between 9 and 1. But you can also just think about it as the coefficients there are equal to 0. Okay, let's see. What about another example of a polynomial? Let's say something like this, 4x cubed plus 2. Okay, also a polynomial that we are familiar with, that's a cubic polynomial. And you can see that there is a common form here. We have all of our powers of x, they're all integers. So you can think about it as integer 1 over here, power 1. Right, and we have real values for the coefficients, and typically we write our polynomials in descendant order of powers, but it doesn't have to be. So if you rewrite it in a different order of powers of x, that's not incorrect. Now let me give you quick examples of functions that are not polynomials. So something like this, 2x plus 1 over x squared minus 4. That's not a polynomial function. It cannot be put in the general form. Okay, we have division of two polynomials, and we're going to consider these functions. They're going to be rational functions, right? And we're going to learn about them in our next lectures. Okay, another example, what's a function that's not polynomial? Let's say cubic root of x plus 1. As soon as you have a radical, right? That is not a polynomial function. Let's see, what else? The absolute value function is not a polynomial function. And anytime you have power of x that's not an integer, so something like 3/4, that's also not a polynomial function. Okay? So now that we know the form, the general form of polynomial functions, we can talk about some basic properties of polynomials. The first thing first is the domain of all polynomial functions, and that's every single one of them, is all real numbers. Okay, so we write from negative infinity to infinity, or you could also write as this double-sided R, and that's very convenient because we don't have discontinuity. We don't really have to think about what the domain is. We know that it's everything. The graphs of polynomial functions are nice, smooth, continuous curves. What does that mean? Okay, continuous, that means there are no rips. Smooth, that means that there are no sharp edges or corners, right? So something like this. That's an example of a smooth curve. Something that's not a smooth curve. Okay, this cannot be a polynomial for several reasons. We have a discontinuity. Okay, we have a rip, right? You can think about it as there's a skip in the graph. And we also have sharp edges. So continuous functions are important, but also smooth, where we don't have drastic changes in the behavior. Okay, let's see. Y-intercept. Y-intercept always exists because we can just evaluate our function at 0. Okay, evaluate at x is equal to 0, and that will give us one of the points. We're going to use that point a lot when graphing polynomial functions. Okay, now what about x-intercept? That is what we do when we set up whatever the function is equal to 0 and solve for x. So later in our lectures we will discuss how to do this, and factoring will be a big technique to determine what the intercepts are. Okay, and here in parentheses I put that they may not exist, right? So we're not always going to get solutions. Graphically, that means we're not always going to get our graph intercepting the x-axis. Okay, local and absolute maxima and minima, so something that we've already discussed, and now we're going to look at graphs and determine where they are. Okay, so we're going to be able to locate these on the graph. And then in calculus 1, we're going to revisit these functions and compute these maxima and minima explicitly. So we'll build in this connection between graphs, functions, and derivatives. So now what I want to talk about is the AND behavior and turning points of polynomials, and I'm going to first create a table that will help you remember how to determine what your polynomial is going to look like. So the AND behavior, that's what we're going to discuss right now. The AND behavior depends on two characteristics of the polynomial. Okay, so degree and sign of the leading coefficient. Okay, so as far as degrees go, we can have even degrees or odd. So let me write it over here, and then here I'm going to write odd. And as far as the leading coefficient goes, plus or minus, right? So in this case, I'm going to write n is greater than 0, so that's positive. And then degree here is even, and we're going to consider negative leading coefficient. And the same over here. Odd degree, positive leading coefficient. Odd degree, negative leading coefficient. Okay, and if you have those two characteristics, that's every possibility that we can discuss, right? Okay, so one of the wonderful things about polynomials is that they behave the same at infinity, meaning as we go far to the right and far to the left, the behavior of all polynomials falls into one of these categories. All right, and that's going to be determined by degree and the sign of leading coefficient. So the first thing we're going to consider is even degree and positive leading coefficient. What's going to happen here? Both branches are going to go up, and then stuff here in the middle, that's going to be different. Okay. Now, one easy function to remember is x squared. So I'm going to put kind of a cheat sheet over here to help you remember how these functions behave. So x squared, the parabola, right? We know really well by now how this behaves. It opens up, okay? And that's going to be the same situation for all polynomials of even degree with a positive leading coefficient, okay? Similarly, if we consider even degree, negative coefficient, so let's just go ahead and flip our parabola. That's going to be our hint, okay? What happens here? the branches go down to infinity as we go to the right or to the left on the x-axis. Okay, and over here I'm putting this dashed line to represent that behavior here will be different depending on what your polynomial is. Okay, but the and behavior is identical for all polynomials of the same degree and same sign of the leading coefficient. All right, now let's take a look at the odd degree polynomials. Now you might be kind of thinking, okay, are we going to use x cubed? Yes, let's go ahead and use x cubed. And here is our behavior, right? So all polynomials of odd degree with positive leading coefficient will have one branch that goes up to infinity and to the right, one down to infinity and to the left, and stuff here is different. Okay, similarly, negative x cubed, you know what that looks like, that's just reflected. So we get this kind of behavior. All right, we have up to the left, down to the right. Okay, and now if you see a polynomial function, you can identify its degree and the sign of the leading coefficient, and then you can map it to one of these scenarios. Okay, so that is the and behavior. Let's go ahead and talk about the turning points. So here I'm giving you a sketch of a polynomial function, and now given the information that we just discussed, we can make a couple of observations. So we have this graph with both branches going up to infinity, whether we go to the right or to the left. So that means this is a polynomial of even degree with positive leading coefficient, right? So let me go ahead and write it here. Whatever this polynomial is, it's of even degree, okay, positive leading coefficient. Okay, turning points, what are those? Those are the points where our function changes behavior from increasing to decreasing, or from decreasing to increasing. So in our case, we have A, B, C, D, and E. On this graph, I have 5 turning points. Okay, so if you were to write intervals where the function is increasing or decreasing, right, you would be using those points to come up with intervals, and that's something we have done for some functions, cubic and quadratic functions, that we've done in our previous unit, right? So what is the connection between the degree and number of points? So for a polynomial, let's say we have f of x, polynomial of nth degree, polynomial of nth degree, whatever that might be, okay, then there are at most, we'll talk about what that means, n minus 1 turning points. Okay, at most means there could be less, right? There could be fewer number of points. So let's say I have a polynomial, here's a quick example, of 7th degree. So let's say something like this, negative 2x to the 7 plus 4x to the 5, and then 4x minus 2. Okay, just a quick example of a polynomial of degree 7. What can I say about the number of turning points? Okay, number of turning points here. All I can say that it's at most 6, 1 less, okay? It could be 1 or 2 or 3 and so forth, right? So 1 or 2 all the way or 6, okay? But it cannot be more than 6, all right? So having said that, now we can kind of see how it works the other way around. So if I have a sketch of this type, I count how many points I have. I have 5 turning points. 5 turning points. I know for sure that this polynomial is of even degree. What is the degree? Okay, the degree for this one is at least 6, right? So we know it's even, okay? But we cannot guarantee that it's exactly 6, because 5 points could also be for a polynomial of degree 8 or 10 or 12 and so forth. So at least 6, that means it could be 6, 8, 10, 12, and so forth. Okay? So let me go ahead and highlight the important part, the important phrase in this definition. There are at most and -1 turning points, and that property is going to be very useful when we're trying to determine the graph of a polynomial, or trying to make a come up with characteristics of polynomials based on the sketch. All right, thank you for watching.